This table will become very familiar to you as we learn a little bit more about redox reactions and go on to electrochemistry this year and then more advanced electrochemistry next year. First of all, just to tell you that these values on the right hand side of the table, you can ignore them for now. They're commonly known as E0 values, and we'll delve more into them next year. I want to explain a little bit about how this table works in relation to the redox reactions you've just learnt about. You know that redox reactions consist of two half reactions, an oxidation half reaction and a reduction half reaction. So this table shows the oxidation and reduction reactions for a particular species and its ions in one line, and that is why you see a double arrow. So if we have a look right at the top, you will see that if we read from right to left, in other words, if I read this reaction this way, this is what it will look like. Li goes to Li plus an electron. But then if I read it the other way, from left to right, it will read Li plus an electron goes to Li. So clearly this blue that I've just written, the lithium ion is gaining an electron, so that is a reduction half reaction. And then if I look at this red, lithium atom is losing an electron. It's becoming oxidized, so this is clearly an oxidation half reaction. So oxidation half reactions are always read from right to left. Reduction half reactions are always read from left to right. Now, I'm going to highlight two sides of the table. First of all of these species on the right hand side. The species that I've highlighted in yellow are reducing agents, with the strongest reducing agents being at the top here. In fact, you will see over here on the right hand side it says increasing reducing ability. Sorry, let me just highlight that instead of crossing it out. So if I highlight that, increasing reducing ability, so if we go to the top of the table, the ones that I've put a ring around are the strongest ones. So the strongest reducing agents are the ones that are oxidized the easiest, the greatest tendency to be oxidized. You will actually think of them from grade 10 as being the most reactive. But from now on, we're going to talk about them in terms of their reducing ability. So, for example, lithium is a stronger reducing agent than potassium, which is a stronger reducing agent than cesium. So, in other words, it's more easily oxidized. Then, if we look at the left-hand side of the table, all of these species over here, those are all oxidizing agents. And the strongest oxidizing agents are at the bottom. So in other words, as we go down the table, you will see that they become stronger and stronger. In other words, they have the greatest tendency to be reduced. Remember, an oxidizing agent gets reduced and a reducing agent gets oxidized. So this also ties up with what I've just said. Because reducing agents get oxidized, that is why they are on the top right hand side, because we are going to obviously read them this way, oxidation from right to left. And then if they are reduced, if they're the greater the tendency they've got to be reduced, we're going to read the table from left to right. So typically they would give you an equation and ask you to balance it using a redox reaction. Now, you know, redox reactions involve the transfer of electrons. So we could balance this by inspection, but that's not what they're asking us for. They're asking us to balance it using a half reaction table. So what we do is we go to our half reaction table. First of all, let's write the oxidation numbers as I taught you, of each species. So aluminium oxidation, it's an element, neutral element, so it has an oxidation number of 0. The Cu2 plus ion in copper sulfate, you know sulfate's -2, so that must be +2. Going to the other side of the table, the aluminium ion is +3, other side of the equation. And then, of course, copper is a neutral atom, so it has an oxidation state of 0. So if we do a quick analysis of what has happened, Al has gone to Al +3, so it's lost electrons, it's become oxidized, and Cu2 plus has gone to 0, so it's gained electrons, it's been reduced. All right, so it's very useful to do this before you go to your table. You will notice that no mention has been made of the sulfate ions. They have not changed on either side of the equation, so they are known as spectator ions, and we don't bring them into the equation, which is quite useful. So then I can go to my SEP table, and first of all, let's start with oxidation. So I go to my table and I go down to aluminium, and remember it's getting oxidized, so I must now read from right to left. So I'm going to write the following. I'm going to write oxidation half reaction, and I'm going to write it exactly how I see it. I see it Al goes to Al +3 or 3 plus 3 electrons. That's exactly how I see it on my table. Now I go down to copper, but now I'm going to read copper ion going to the copper atom from left to right because it's a reduction. So I write reduction half reaction, and I go to the left hand side of my table and I find Cu2 plus, and I read it off exactly as I see it, write it exactly as I see it, +2 electrons reacts to form Cu. Now with a redox reaction, you have to balance the electrons first because it is a transfer of electrons. So you will notice we've got 3 electrons in the one and 2 electrons in the other. Now they don't balance out. 3 doesn't go into 2, 2 doesn't go into 3, so we need a lowest common denominator. So what I'm going to do, I'm going to times this whole line, this whole equation by 2, so that we get 6 electrons, but I also have to put a 2 there, and I have to put a 2 there. So how do I get 6 electrons with the next one, the redox half reaction? I've got to times that by 3. So I get 6 electrons there, but I've also got to put a 3 here, and I've also got to put a 3 here. Now, the first thing you look at is the electrons. We've now got 6 electrons on one side, 6 electrons on the other side, so they balance out. I can now write my full ionic reaction as I see it, 2Al plus 3 Cu2 plus, because those are both on the one side of my reaction, reacts to form 2Al3 plus 3 Cu. Those are on the other side of my reaction. So that is my full balanced ionic reaction, balanced using redox reaction.